Water hammer is not just a hydraulic concept, it is a risk management issue in pipeline design. In this video, I will explain how we calculate water hammer, how we analyze system response, and how we design it to prevent failure. First off, we have to understand what water hammer really is. When water is moving in a pipeline, it has momentum, and any sudden change in velocity creates some pressure wave. Now that wave travels at very high speed and is what is reflected at the boundaries of the pipes, causing burst, ruptures, and some other risk goes onto the pipe. So let's look at the fundamental calculation which is used to do water hammer analysis. Now we just take use of Joukowski's equation to analyze our system. This is a very simple equation which takes care of our water hammer system. It uses the equation H equals to VCP over G, whereby the H is the water hammer in meters, the V is the average velocity before rapid stoppage or closure, and then the CP is just the wave speed. It normally ranges between 200 to 1400 meters per second, which depends on the physical characteristic of the pipe of the main line. As we know, G is acceleration due to gravity. So when we're doing this optimization, we have to take care of all these parameters to make sure that our system is well performed. So from this equation, I want you to notice something very important. The site pressure depends directly on the velocity change and the wave speed. And wave speed depends on fluid compressibility, the pipe material, the pipe wall thickness, as we're going to look into our example. So assuming incorrect wave speed is one of the most common errors in such estimation, but as I said, our wave speed ranges between 200 to 1400 meters per second, so take that into consideration when you're doing your design. So let's just take a numerical example and we see how the system is performed. So let's say you have your pipeline, your system, transmission line having an HTP pipe, ordinary diameter of 0.08 meters, that is 80 millimeters ND, and having internal diameter of 0.079, and the pipe is stretched. It has a length, the transmission line has a length of 3 kilometers, that is 3000 meters, and then the flow velocity in the transmission line is 1.1 meters per second. So from this system, through preliminary sizing, we decided to use a pipe with a working pressure of 100 meters. Our water density is 1000 kilograms per cubic meter. Our acceleration due to gravity is always 9.8 meters per second. So the speed of sound in water, which is the CW, and from this equation, the CW comes from the calculation of the wave speed. So wave speed equals to CW over 1 plus bulk modulus of water divided by modulus of elasticity of the pipe wall material times the diameter, internal diameter, divided by the thickness of the pipe. So our speed of sound in water ranges from 1400 to 1500. So for our design, since we want to optimize the system well, we are going to choose 1500 as our CW value, and then the bulk modulus of water is 1500, and the Young modulus of elasticity of the pipe material is 800. So our pipe thickness is 0.055. So from this, we are supposed now to compete for water hammer. Now how best can we compete for the water hammer? Now from the equation, we are supposed to look for the value of CP, because our equation says water hammer is V CP over G. So the CP is the wave speed. So we are going to calculate for it and get the real value, because the value is supposed to range between 200 and 1400. So we are yet to find out through our calculations. So CP equals to speed of sound in water. So CP, the speed of sound in water, which ranges between 1400 to 1500, and me I adopted 1500, which is this. All of it divided by 1 plus bulk modulus of water 1500, which is here, divided by EP. Our EP is 800 times the diameter of the pipe. The diameter of the pipe, the internal diameter of the pipe is 0.09, divided by T, the thickness of the pipe, which is 0.05. Now from this equation, we get 406.2 meter per second. And now this is the value we're going to come and confirm and cross-check with the wide range is supposed to be between 200 to 1400, and since I was falling within it, it is okay. Now from there we can bring this equation up here, this value of the equation up here, and then let's try to do our calculation on the water hammer. And since we said water hammer using the Joukowski's equation, it is VCP divided by G. So water hammer, it is V. Our V value is the velocity, which is 1.1 times the CP, and our CP is the surge velocity, which we just calculated, which is 406.2, all divided by G, acceleration due to gravity, which is 9.8, and this gives us a value of 45.5 meters. So any sudden closure or instantaneous stop into the system is going to cause a drop or a surge of 44.5 meters, which if we change into bars is 4.45 bars. Since 1 bar equals to 10 meters, this is 4.45 bars. Now another important component to look at the system is the wave travel time. How fast the wave travels into the system. And now to calculate the travel time of the wave, it is basically the distance of the pipe, or the pipe length. It is a pipe length divided by the surge velocity, which is 3000. Our pipe length for the transmission line divided by surge velocity, which we calculated as 406.2, and this gives us a value of 7.4 seconds. Now to avoid any surge into the system, we have to make sure that the wave travel time, or the TC, is equals or greater than the 5 TC. So to the closure time of the valve should always be greater than 5 TC, greater than the wave travel time. So that means this one here we multiply by 5 multiplied by wave travel time, which is 7.4. It gives us a value of 36.9. So now how do we do the analysis here? This is the most important part, because this is where you make engineering judgment. So our system, we said we are going to use a pipe, the pressure rating of 100 meters. So we adopted a PN rating of 100 meters, but our allowable surge can range between 1.3 to 1.5 of the PN rating of the pipe. That gives us a range of 130 to 150 meters. And since our computed value is 44.5 from the equation, 44.5 meters, it means the surge which is generated in the pipeline can be contained by our selected pipe of PN10. Now closure time, or the wave travel time, it is something very important. Once we calculate that, it's going to help us to guide on the type of the device you are supposed to adopt. So the T closure time is the 36.9. We are going to look at the type of valve that you are supposed to use. It helps us to decide on the type of valve that we can use, and from this table we can see that the best valve we can use with that range, our value is 36.9 falls between this first gate valve. So we are going to use the gate valve, since it has a typical closure of 30 to 90 seconds, and our value is 36.9. So this makes sure that our system is safe. We can't use butterfly valve or motorized valve or another check valve, because they are not falling within the required parameters. So from here we come to realize that we are going to use a gate valve in our transmission main. So from this we know that the PN10 is capable of containing that pressure which can happen on the transmission line. So from this equation as well, you can see PN10. So since our value was 44.5 meters given a pipe, PN5 can also accommodate the system, but because we want to minimize on the risk, we can adopt PN10. But that is how we do a basic calculation to the system. So from here we can learn that material selection is not only structural, it affects hydraulic transients. So while as an engineer, after this calculation, you're supposed to know how to choose the type of pipe you're going to use. But for complex transmission systems, simplified equations are normally insufficient. So we will be required to perform full transient modeling for our system. The real failure mode really happened in our transmission main through various ways. First one is the pipe rupture, where the pipe is just ruptured as it says, and the second one is joint separation, where through the build up of the pressure onto the joints, and the joints, they tend to separate themselves from each other. And also at the same time, this same water hammer impact also affects the anchor blocks that we use to support our pipes at the junctions or at the bends. So all this should always be taken care of. So just like how I give an example how we mitigate this problem using selection of the right pipe pressure rating, we can also do the same thing on other components. Instead of using pipes, we can adopt such tanks, air vessels, slow closing valves like we looked at, or pressure relief valves. But those mitigation measures must be economically justified, because over design always wastes capital, and under design risks catastrophic failure. So we have to look into a way of cutting across into between the two of them and make sure that our system is sustainable, is economically viable, at the same time is structurally sized. If you like more of this, make sure you subscribe. See you in the next video.